So, in our last video, we have discussed about two experiments in which we have in one experiment we have interference, and in one experiment we don't have interference. So, if you remember in bullet experiment, when this gun is electron, not an electron gun, but let me see. Okay, so now we have a new uh, experiment with electron. So for this experiment, we replaced our uh, gun with electron gun, which sprays electrons. Then after we have a wall having two holes, one and two, in same way, backstop, a detector. So we consider that all electron which are entering from here have nearly same energy. Okay, and this movable detector is, let's say it is a giga counter or electron multiplier connected with loudspeaker, and every time an electron is detected by this detector, it sounds click, 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 click sound. So these clicks are very sharp clicks. There are no half clicks. Okay, and number of clicks for a particular time is always nearly same. So in our step 1, when we block our hole 2, but hole 1 is open, so we get this P1 curve over here, which is similar to our first experiment graph. Now in step 2, when we close this hole 1 but hole 2 is open, then we get a P2 curve similar to our first experiment we already discussed in our last video. So what we see here, that when both holes are open, we get this new graph, which is not a probability graph similar to our bullet experiment. Instead of that, it is similar to our wave experiment when both holes are open. So let's see how can we explain it. We will discuss it in our next slides. And one more thing I would like to add here, that number of clicks for a particular time is always nearly same. So now what there are some other points like rate of clicks may appear faster. Oh, let me go back. A rate of clicks may appear faster or slower, but loudness of size of clicks is always same. This is one more point that we observe in our experiment. Now, at lower temperature, rate of clicking slow down, but each click sounds same. Okay, you can say these are our observations. So now, when two detectors at backstop, when we replace our that detector with this detector over here with two detectors, okay, so one or other would click, but they never click both together. So we obtain a relative probability by observing the rate of clicks uh, by holding the operation of the gun. Now let's understand this result, that how why we are getting this interference over here. Should we say this is more like wave? So let's discuss it. So uh, before starting this, uh, we have a proposition. We say electron either goes through hole 1 or hole 2. Okay, that's easy. Now, for further discussion, we say if electron through hole 1, then uh, uh, hole 2 is closed and hole 1 is open. So we get P1 probability and P1 curve, as you can see. In same way, when electron go through hole 2, when hole 1 is completely blocked, we get probability P2 and P2 curve, as you can see. So our observation curve must satisfy this condition according to our intuitions. This must be satisfied. But in our experiment, we can see that it is not equals to P1 plus P2, because you know P1 plus P2 must give a curve like this. Okay, a simple mountain. So a result P1 to obtain with both hole open is clearly not the sum of P1 and P2. So in analogy with our water wave experiment or wave experiment, which we discussed in our previous video, we say there is interference. But how can we explain it? So how can such interference come about? So it is not true that lumps go either through hole 1 or hole 2, because if they did, then probabilities must add. So I think we can see they must have some complicated path. Okay, so there are some point at which very few electrons arrive when both holes are open, but which receive many electrons if we close one hole. So closing one hole will increase the number from other. So this is one of our observation also. So we can say they must have some complicated path. So as you can see, we cannot define it physically or our by our intuitions. So we take help of mathematics. So mathematics for relating P1 and uh, relating P1 and P2 to P12. As you can see, this result is not correct. So we must relate them. So let's say this P12 is just like I12, which we discussed in our wave experiment. Okay, so this P12 is similar to I12. Okay, and this phi1x and phi2x are two complex numbers whose squares corresponds to P1 and P2 respectively, and uh, we introduce here phi1x and phi2x so that we can relate these probabilities P1 and P2. So we can say these phi1 and phi2 are amplitudes, and also they are complex numbers. Okay, we will discuss it in later slides. So conclusion is that the electron arrives in lumps, okay, like particles, and the probabilities of arrival of these lumps is distributed like distribution of intensity of wave. It is in this sense that an electron behaves something like a particle and sometimes like a particle and sometimes like a wave. So here we suggest that They sometimes behave like particle and sometimes a wave. So in our quantum mechanics, it turns out that amplitude must be represented by complex number, which I already mentioned. But for now, our proposition is false. Let's move ahead. Now, what we try in our previous experiment, we didn't bother about the uh, the electron. So this time we try to watch it. So this is the same setup, but here we have a light source. So we have a light source over here. Okay. So this extra light source behind the wall and between the holes. Now, whenever an electron pass through, these electric charge scatter light, and when they scatter light, we see a flash. Okay, every time we hear a click, so we see a flash of light either near hole 1 or hole 2. So let's say, uh, for example, electron passes through hole 2, and when it crosses through this distance, we see a flash of light, and same time we hear a click. Okay, so we get same result no matter where we put our detector. So conclusion is that we concluded when we look at electron, we find that electron either goes through hole 1 or hole 2. Okay, after that we follow all those steps, like for step 1 we close our hole 2 and hole 1 is open. Same way step 2, hole 2 is open but hole 1 is closed. So we get these distribution curves like or probability curves p dash 1 and p dash 2. But this time when both holes are open, we get a curve like this, which is similar to our first experiment, in which we see when bullet are passing through, when both holes are open, we get this kind of curve. So here p dash 1 2 is equals to p dash 1 plus p dash 2 is true. So we concluded when we look at electron, we find that electron either goes through hole 1 or hole 2. So experimentally, proposition A is necessarily true. So let me clear one thing, that whenever I'm trying to watch the electron, our proposition that we uh, have in our last slide, that uh, okay, that must be over here, that electron either goes to hole 1 or hole 2. Okay, so that proposition stands true over here. Okay, now what then is wrong with our argument against proposition A? Why isn't P12 just equal to P1 plus P2? That is our experiment when we don't try to watch the electron. So tracking of electron, we get a curve P dash 1 which is approximately equals to P1, and P dash 2 which is approximately equals to P2 for repeating measurements for many values of x. So here in column 1 we take a record whenever we hear a click sound and electron coming from hole 1, and for this column 2 whenever we hear a click sound and electron coming from hole 2. So when we watch them, the electron come through just as we would expect them to come through, whether the holes are open or closed. So let's say we never looked at flashes and we have data. This p dash 1 2 equals to p dash 1 plus p dash 2 must be true. So we no more find interference in p dash 1 2, but if we turn off this light source, p12 is restored. So what is p12? So p12 is phi1 plus phi2 whole square. Okay. So conclusion, we must conclude when we look at electron, the distribution of them on screen are different than we do not look. So the light exert a big influence on electron. By trying to watch the electron, we have changed their motion. This is our takeaway for these experiment, what we can have our like result at the end. So the light exert a big influence on electron. By trying to watch the electron, we have changed their motion somehow. So let's replace our light source with dim light. Okay, same experiment, but now this light source which was over here, now we replace it with dim light source. So what we observe that flashes does not get weaker, we get same size flash. So sometimes click sounds from detector but no flash to track. This must be noted. So it is true that whenever we see the electron, we see same sized flash and they are distributed. Sorry, they are disturbed one. So what I want to say here that it is true that whatever we see, the electron we see same size flash and they are disturbed one. So we have this column over here for that experiment when we have this light source dim. Okay, so in column 1 we are going to write p dash 1. So electron seen by hole 1 comes under this. Column 2 p dash 2 electrons seen by hole 2 come under this, and those electrons not seen at all comes under p12. So those seen by either hole 1 or 2 have distribution like p-12, but those which are not seen by either of holes have distribution like p12. So this p-12 have no interference. Okay, but this p12 has interference. So those which are not seen are similar to p12 and they suggest interference, but p-12, which is just sum of p-1 and p-2, is suggesting that there is no interference. Now let's move ahead. This might get quite confusing. So if you find any confusion, you can comment and I'll try to solve. So if electrons are seen, they exhibit interference. So I think I have written it wrong. So what we see, let me, if, okay, electron seen means no interference, but electron not seen means interference. So if electrons are seen, they exhibit, I, here must, here I have to write, okay, it will take just 1 second, no interference, otherwise if they are not seen, they do not if they are not seen, they do exhibit interference. Okay, so I think this is correct. So if electrons are seen, they exhibit no interference, and if they are not seen, they do exhibit interference. Okay, let's move ahead. So, is there not some way we can see electron without disturbing them? So now this is a question that might pop up in your mind. So for this, we try our experiment with low frequency light. Now, for example, we replace our light source with a redder color or IR light, a radio wave, etc. Now, repeating our experiment each time with longer wavelength. So, at first, nothing seems to change. But as we lower frequency, means if we lower the frequency, we are increasing the wavelength. Okay, so we see a big fuzzy flash. We can't determine now where did flash come from. So let me clear it. So this is our light source. So if its frequency is very low, means lambda is long. So what we observe here, a big fuzzy flash. Okay, but we can't able to determine that it is from hole 1 or hole 2. Okay, so uh, it is only for wavelength much longer than the separation of two holes. So if hole 1 and hole 2 are separated by, let's say, length d, and lambda is greater than this d, so this point is correct for uh, this situation over here. So it is only for wavelength much longer than the separation of two holes. So disturbance due to light get sufficiently small that we again get the curve P12. So as we increase the wavelength, so disturbance decreases and electrons again exhibit the interference. You must remember that P12 in our electron experiment is for interference curve. Okay, so it is impossible to design an apparatus to determine which hole the electron passes through that will not at the same time disturb the electron enough to destroy the interference pattern. That must be noted. Okay, so what about our proposition A? Should we say our proposition A is wrong or correct? We can see that whenever we try to watch the electron, we find our proposition A stands true. Okay, but whenever we don't try to watch the electron, our proposition A stands false or not true. So I have to say it like that. If one looks at the holes, or more accurately, if one has a piece of apparatus which is capable of determining whether the electron go through hole 1 or hole 2, then one can say that it can goes through hole 1 or hole 2. But when one does not try to tell which way the electron goes, when there is nothing in experiment to disturb the electrons, the one may not say that electron goes through hole 1 or hole 2. So this is the same thing that if I try to see the electron, proposition A is true, but if I don't try to no see, not try to see, So our proposition A stands false. Okay, that is what I have written here. So we have to say this is the logical tightrope on which we must walk if we wish to describe nature successfully. Now, in summary, what we have understood that the probability in an ideal experiment is given by uh, this. So, and for this, now we have a phi, which is a probability amplitude, and we discussed about it that in quantum mechanics it must be a complex number. So P must be equals to phi square. Okay, this is the first point to be remembered. So when an event can occur in several alternative ways, so this is same simple probability case that we have to add the amplitudes first, then square it. So phi 1 plus phi 2 whole square when event can occur in several alternative ways. So third, if an experiment is performed which is capable of determining whether one or alternative way is actually taken, so we have to just add up p equals to p1 plus p2. So let's move ahead. This is, I think, our second last or last topic, which is uncertainty principle. I think you might have heard about it. So I'm just reading the statements. So if you make a measurement on any object, let me clear it. If you make measurement on any object and you can determine x component of its momentum with an uncertainty of delta p, you cannot at the same time know its x position more accurately than this factor. Okay, so where this h bar is fixed number given by nature, also known as reduced Planck's constant, and which is approximately equals to 1.05 into 10 raised to the power minus 34 joule second. So in simple sense, one can't design equipment in any way to determine which of the two alternatives is taken without at the same time destroying the pattern of interference. Okay, this is the uncertainty of principle. It's like a base of our quantum mechanics. So if this principle fails, everything shatters. So question is that if the motion of all matter as well as electrons must be described in terms of waves, what about the bullets in our first experiment? Why didn't we see an interference pattern over there? So answer is quite simple, that wavelength were so tiny the interference pattern became very fine, matlab, very tough to differentiate. So in fact that with any detector of finite size one could not distinguish the separate maxima and minima. What we saw was only a kind of average, which the classical curve, this p12. So the rapid wingles are supposed to represent the interference pattern one gets for waves for each short wavelength. Any physical detector, however, straddles several vehicles of the probability curve so that the measurement shows the smooth curve. So for our bullet case, uh, interference this is the curves over here and its average is smooth out over here p12. So that was all about this chapter. So if you find it difficult to understand, so please comment in the comment box. I would like to um, I will be happy to answer your questions, and I might have stuck on some points, but let's study together. And whatever you find something missing out, you can just comment it. Thank you so much. We'll meet in next video, which must I think that will be our chapter 2.